Good morning, everyone. On behalf of the Research Institute for Diagnostic Accuracy, I'll be presenting the recent research developments of our institute. We all know that with the implementation of lung cancer screening, a large volume of CT scans are going to be produced. And this is why we've seen over the years that there are many AI systems and lung cancer prediction tools that have been developed, and they're actually increasingly used to support pulmonary nodule detection and participant selection. However, we do see that the independent validation of those AI systems remains limited, and especially for the detection for the reference lung nodule. So today I'll be walking you through two complementary projects. The first one is the comparative analysis of different AI systems for the reference nodule detection. And the second project will be looking into the validation results of CBIL, which is a lung cancer risk prediction tool. So first we start with the comparative analysis of four AI systems for the reference nodule detection. And for this project, we use 4C certified AI tools. The data that we use for this project came from the Foreign in the Long Run trial. It's a European implementation trial that actually looks how we can implement lung cancer screening in a cost-effective and clinically meaningful way. We selected participants consecutively from 3 screening centers, and we used the reference standard of the expert panel consensus. The participants aged between 60 and 79 years of age, and they were heavy smokers, so equal or over 35 pack years. And on the right side, you can see how the data set was looked like in terms of nodules, of nodule presence. And since we wanted to have it imitate the lung cancer screening population, around 50% of the data set had no nodules or had nodules below 30 cubic millimeters. Then there were some. Then you see we also included some nodules, participants with nodules that from 30 to 100 cubic millimeters, some 100 to 300 cubic millimeters, and some participants that had large nodules of over 300 cubic millimeters. The reference nodule definition here was a nodule that was solid and over or equal 100 cubic millimeters. And we, of course, included some morphological criteria. So, for example, we did not include any peripheral nodules and non-solid nodules. And to make it similar for us to analyze the results, we used the 100 cubic millimeter threshold. And we grouped, we had 2 groups. We had the group of participants that had no nodules or nodules below 100 cubic millimeters. And when we ran those scans through the AI, and AI detected no nodules or nodules that were below 100 cubic millimeters, then that was a correct negative. And when AI detected a large nodule within this cohort that was over 100 cubic millimeter, then that was a positive misclassification. And then if we go over the wall of the 100 cubic millimeter threshold, we have the reference nodule cohort. So the participants that had a reference nodule that was greater or equal to 100 cubic millimeters. And when AI detected the reference nodule, then that was a correct positive result. And when AI did not detect the reference nodule, then that was a negative misclassification. And you see here the results. This is the overall performance of the 4 AI software. This is the non-reference nodule classification, so the 477 participants that had no nodules or nodules below 100 cubic millimeters. You see the software B and software C had a similar or the same performance. So they all had the same numbers of correct negatives and the same number of positive misclassifications. Software A and C. So for example, software A had more correct negatives than software D. And software A also had less positive misclassifications than the software C, software D. This is the reference nodule classification results. So how many reference nodules did those AIs eventually detect? So you see that software B detected 71 out of 77 reference nodules and has 6 negative misclassifications. Then software D had 11 negative misclassifications and detected 66 out of the 77 reference nodules. And then software A and software C had similar performance. So the conclusion from this project, which is of course ongoing, but these are just the results from the first phase, we did see some inter-software differences. There was a performance gap between the C-certified AIs. And we do believe that there's a clinical risk when an AI is implemented in a clinical space without being validated and without being continuously validated, of course. And we saw some preliminary results of performance, which depends on anatomical and morphological variability. For example, we did see some differences in detection of nodules when nodules were present on the right lobe of the lungs. And then we can move on with the second part of the second project that we're presenting today, and that's the validation of the deep learning model CBIL for lung cancer risk prediction. So I think you've all heard of CBIL by now. The first publication came out in 2023. It's a deep learning lung cancer risk prediction model that actually has an output of a lung cancer risk, and for year 1 to year 6 after one CT scan. And it can also produce attention maps. So the attention map is an overlay, is a red overlay of the initial CT scan, and you can see it on the right. And it basically highlights the nodule or an area that a nodule might appear in the future. CBIL has shown potential based on publications that can be integrated into the clinical workflow of lung cancer screening. And it was developed by MIT. The challenge for CBIL is known. There's a need for extension validation before clinical implementation, of course, in various scenarios. And the scenario we're testing today is lung cancer screening. The objective of our study was to see what is actually CBIL's clinical applicability within lung cancer screening, and how are the year 1 risk scores related to year 1 histology confirmed cancers. So these are the methods that we used. So we performed the validation of CBIL according to the initial application of CBIL, so Michael et al. We used the UNOS concordant index and the area under the curve for each year for up to 6 years. And these are very standard metrics for lung cancer prediction models. So the AUC actually measures how well the model separates participants who will versus won't develop cancer within a given time. And the UNOS C-index actually measures how well the model ranks participants by their future lung cancer risk over time, accounting for timing. So for CBIL, we used low-dose CT scans from the United Kingdom lung cancer screening trial. We used 1,200 participants. They were aged between 50 and 75, and they were high risk for developing lung cancer. And we used only the baseline CT scans. And within the baseline of UKLS, we know that there were 30 cancers. There were actually a tiny bit more, but for research paper purposes, we had to have a matched nodule, therefore we included the 30 cancers at baseline. So the whole analysis, we did it independently from visible nodules, taking into account how CBIL can be used. And we didn't use any nodule volumes. These are the results for year 1 lung cancer prediction for the area under the curve for CBIL. So you see the AUC for year 1 was 0.94, shows a very good performance in terms of separating participants that have cancer versus who don't. The UNOS index is 0.87. And that's also a very good performance based on how well the participants are ranked by their future lung cancer risk over time. This is the ROC curves, AUC curves for years 1 to 6. And you see that there is a sustained performance across 6 years. So year 1 starts with 0.94, and then year 6 is 0.87. And you see a gradual decline in the AUCs. And then we still wanted to see how do the risk scores look like in terms of the confirmed cancers. So what is the minimum score received? And therefore, we plotted this graph. So you see the cancers, the confirmed cancers on the x-axis and the risk score on the y-axis. And for the sake of the baseline validation that we did, you can see that the risk scores of SIBO ranged from 0% to 77%. And after we saw this, we wanted to understand better what is actually, how does it look like in terms of the attention mobs. So we went through all the 30 cases of cancers, and we really tried to assess how they look like and if SIBO really found the nodules. The nodules were indeed, they had a highlighted area. SIBO highlighted the area of the cancers within our cohort, but the absolute scores, the risk score was not really clinically coherent, which means maybe the score was not affected that much from the attention mob. Of course, the year 1 risk when compared to confirmed lung cancers shows variability. And maybe the AUCs could be that they can be inflated when we use imbalanced data sets, because screening data sets only have 1 to 2% of lung cancers. Therefore, we try to find the optimal SIBO risk score. And for this, we found, this is a large table, but we tried to plot the true positives, true negatives, false positives, and false negatives based on the given SIBO lung cancer score. So the first score that actually caught all cancers was 0.02% and 0.2%. So in those two scores, we have all cancers found, but we do have a lot of false positives. So 700 positives, false positives are increase the workload of radiologists dramatically. Then if we go in the middle a bit, we see that 2.16% to 5%, we do have, SIBO does find 27 to 24 lung cancers, but there are still 3 to 5 cancers missed. And then if we move to the larger scores, then we see that with 77%, SIBO finds 1 cancer, but then the rest of the cancers are missed. And of course, we don't have any false positives here, but of course, the 29, 28 false negatives is quite high in this sense. This is just a graph of how the risk threshold is related to sensitivity, and it represents the table I just presented. And then we use the Udens J score. It's basically a trade-off between sensitivity and specificity to choose the best SIBO threshold that we can use, or the SIBO threshold that is applicable. And that score was the 2.16%, which means every participant that has a score of equal or greater than 2.16%, then there should be an action that we don't really know yet. And with this score, we have 27 true positives, and we have 3 missed cancers, while there are 147 false positives. And to conclude with the second project as well, so the AUCs, plotting an AUC as a metric is useful, but of course the histology results should be available. The attention maps of SIBO seem to have little influence on the risk score, but that of course needs further investigation. The optimal threshold within our cohort was greater or equal than 2.16%. And I would like to close this presentation with one question. Because it's an ongoing project. So if SIBO is applied in hospitals, in radiology departments, should CTs with a greater or equal score of 2.16% be referred to a screening program or to a radiologist? Thank you for your attention.